Okay, so here's where we were last time. We were talking about these symmetry theorems. Well, specifically, we were talking about this symmetry theorem here. So a quick reminder of what it says. If you were looking at an integral that you need to evaluate for whatever reason, a couple of things to check. If the domain is symmetric, this domain here, that is symmetric over a certain line. If the integrand has odd symmetry over that same line. So now I emphasize the line of symmetry for the domain and the line of symmetry for the function. They have to be the same line. Right? If this happens, these two conditions are satisfied, then it's the world's easiest kind of integral to evaluate. The answer is 0. Right? So wonderfully convenient, powerfully convenient, I'll say again. You know, I mentioned last time my sort of based on my memory, completely unscientific, very approximate memory of my days evaluating integrals way back when doing physics. I was about 20% of them were susceptible to this argument. Right? And so 20% of the integrals that I had to compute, I didn't have to compute. I just had to observe, oh, hey, look at that, those conditions. Yeah, that's symmetric over this line, I'm done. Right? Very, very, very cool. So we proved this theorem last time. It's this argument down here. It is ultimately a use of change of variables. We find ourselves in a circumstance where we view our domain as being the image of what I'm going to call another domain, but of course it's the same domain. That's kind of the point. It's a symmetric domain. And then just applying the pullback rule, we end up with this, which simplifies to that, which of course is this, and there you go. This integral is the negative of itself, and therefore the integral is 0. So real easy, straightforward proof. By the way, while we're here, let me go ahead and state the theorem in 3 dimensions. Very, very analogous. If the domain is symmetric, if the function has odd symmetry, very familiar sounding. These are, of course, in 3 dimensions now instead of 2. Same 2 conditions, though. Symmetry of the domain, odd symmetry of the integrand. Again, it's got to be over the same plane. Right? You can't have one plane of symmetry for the integrand and a different plane of symmetry for the domain. That absolutely useless, does not work. But if you have both conditions met over the same plane, your integral is 0. Again, world's easiest integral to compute. Okay. All right, so I'm going to show you a couple of examples. By the way, the proof of this 3-dimensional version is morally equivalent to what we wrote right here. It's almost exactly the same, just the 3-dimensional version of this. You might think that through. But anyway, let's see some examples. So suppose, as might reasonably come up, I find myself looking at this function, and I want to do a double integral over the unit disk in the xy plane. Now I've got a domain, I've got an integral. Excuse me, I've got a domain, I've got an integrand, and I want to compute the integral. Your knee-jerk reaction is to say, okay, well, we'd better start slicing up that domain, right? I would suggest that from here going forward, you interject a new step in your procedures, right? When you find yourself looking at an integral. Step 1, ask yourself, hey, any chance there might be a symmetry I can take advantage of here? Because wouldn't that be nice? Right? And so very often you'll look at your domain and it'll be clearly not symmetric. At which point, okay, it was just a thought, right? And then you move on with slicing it up and et cetera, and it's fine. Okay. But sometimes you will find yourself with an opportunity. Disks, of course, are highly symmetric. Okay. All right. So I'm going to make this argument over the x-axis, and I'll come back and talk about why that is in a couple of minutes. But for the moment, let's think about the mechanics. So over the x-axis, what does it look like to reflect over the x-axis? Let's draw ourselves a little picture. There's our picture, and if I have a point x comma y, if I reflect over that x-axis, reflection over that x-axis yields that point. It's not hard to see that the point x comma y, when you reflect it, the reflected image is going to have the same x coordinate, but the y coordinate is going to be the negative of what it had been. Right? Everybody happy with that picture? Pretty believable. So, heads up. It's real easy and tempting to step on the following landmine. Oh, I'm reflecting over the x-axis. I'm reflecting in the x direction, people sometimes want to think. And then they reflexively think, oh, well, that means that it must be x that gets the minus sign. Well, it's just not true, right? So don't fall for the sort of semantical line of reasoning, which is nonsense. Make sure to think it through, and likewise, if you're reflecting over the y-axis, it's the x coordinate that gets the minus sign. Okay, heads up. Okay, so there's a formula for our reflection, and notice our function here. This function really does have odd symmetry over that line. I can demonstrate that by computing f of the reflection and getting the negative of the otherwise value of f. And it's a straight up calculation. Here we go. I'm going to plug the reflection into the function f. Here's our formula for reflection. The reflection of x comma y is x comma negative y. Now, how do I compute f of something? Now, be real careful with this. This is where a lot of students mess up. A lot of students conflate the dummy variables that are being used here to describe what the function does with what's actually going into this function. And tragically, we are using the same letters here, so that is genuinely confusing, right? But make sure to interpret this as it's intended. These are only intended to describe dummy variables. This says what we've got is a function which, look, if you put in two coordinates, whatever they are, that first coordinate gets squared. That second coordinate gets cubed, and then you multiply. It is not intending to suggest that whatever you put in here, whatever they might happen to be called, right? That this little string of characters is the output value of the function. So you've got to be careful with that. So along these lines then, with the first thing that's going in being x, then it is x squared that I get out there as the first factor. But wait a second though, now it is negative y. That is the second coordinate going into this function. Not y. It's negative y that goes in. This says that whatever that second coordinate is, that gets cubed. Right? So what this second factor is coming out is negative y cubed. I'm going to take a pause on that. Is everybody happy? Is everybody on board with that? Okay. All right. Okay. Right, so then negative cubed is negative, and sure enough, this other x squared y cubed, that is exactly f of x comma y, and so as required, f of the reflection is the negative of the otherwise value of f. Okay, so and then the other thing I have to observe over the x-axis, the domain is symmetric, right? The domain's a unit disk. The unit disk is obviously symmetric over the x-axis, and we're done. This integral is 0. That's all that has to get done here. Okay, didn't slice up anything. Didn't do any antiderivatives. It's awesome. Okay. Now, how y'all are going to use this on exams. I sent an email out about this yesterday. The topic came up in office hours yesterday, and then it occurred to me I better make sure that everybody gets the same message on that. So the rule is, in Math 212, force the second exam if you're going to use a symmetry argument. you have to tell me, what is your line of symmetry? You got to indicate that clearly. Okay. You have to show the formula for reflection over that line. Plane, if it's three-dimensional. You then have to plug in and show that the function indeed is odd. I need to algebraically see that. It is not sufficient to just assert the function is odd. Right? At this stage, I want to make sure that everyone can explicitly demonstrate why these things are true. Okay. And finally, you have to state that the domain is symmetric. You do not have to demonstrate that. That is one of these things that, as we're going to use it here in this course, it's sufficiently clear, or it's sufficiently clearly true or sufficiently clearly false in any given case, and it's fine. You can just state it. You do have to be correct, right? You can't just assert something is symmetric if it isn't, right? But you don't have to explain why. So these are the four things that you have to, if you want full credit for a symmetry argument, you got to tell me, what is the line or plane of symmetry? What's the formula for the reflection? Explicitly confirm oddness and correctly identify symmetry of the domain. Any questions about that? Yeah.
If we don't use the symmetry argument, just do it out, will that be okay?
So this gets into a philosophical gray area, right? So keep in mind what the purpose of an exam is. The purpose of an exam is for me to gauge your proficiency with the ideas of the course, right? So a way to go about doing that is for me to say, okay, well, I'll make questions, and if they understand the material, they'll be able to get the correct answers. And if they don't understand the material, they won't be able to get the correct answers, and so we'll just go on the basis of correct answers, right? So, and of course, we're not going to do that. So, what we're doing here, keep in mind, is I am looking at the explanations, the thought that you communicate on your paper, and I'm gauging the quality of that thought. So ways that thought can be of lower quality. One way is it can be wrong, right? It can be incomplete. It can be awkwardly phrased, right? These kinds of things are all not as good. And another way that a line of reasoning can be not as good as a different line of reasoning is for it to be unnecessarily difficult. Right? So if there is a symmetry opportunity, and if instead you fill up a page and a half of dense, tedious algebraic calculations, well, yeah, you missed a good opportunity there. And no one would voluntarily do it just a whole bunch of algebra, right? If someone does a whole bunch of algebra unnecessarily, it's because they didn't notice or something they didn't see or whatever. So I'm gonna say that, I wouldn't count off a lot, right? But I would not be obligated to give full credit. I might give like 9 out of 10, something like that. If you did it the brute force way when you could have used a simple symmetry argument, maybe 9 out of 10. Yeah. Great question. Thank you for that. Anybody have any, does that make sense, by the way? Yeah. Okay. Anybody else? Yes. Yeah. If it's a weird lumpy shape, like if it's one of these monsters, if it's one of these things, like here, yeah. I'm sorry, one more time.
So if it's something like that, this could most likely be able to use one of the techniques.
Yeah, if the domain is like this, so another, so a point of view that y'all can capitalize on is, again, I'm not a monster, right? And so if I give you a domain that looks like this, per the Bray is not a monster argument, that can't be a slice it up straight, good old rectangle, because again, that would violate the Bray is not a monster rule, right? So, that's your strategic tip off that, there's probably a clever way to do this. Change of variables is a good candidate. Right? We're going to talk about some other methods today that would also be good candidates. All questions that I give you on an exam should be, reasonably achievable. And by the way, I do work out the solutions myself before the test. Before I copy the test, I have the solutions all worked out, and I make sure that they are, convenient as I hoped they would be when I wrote them. Yeah. Okay, so let's see here. So now here's another example. And the purpose of this example is to give you a warning. So let's suppose we want to compute a double integral, and we've got this function. Oh, hey, it's the same function that we had previously. Oh, so that's got odd symmetry. How nice. Cool. Let's see, our triangle, our domain is this triangle, and it has vertices there, and there. Let's draw that real quick. That triangle has vertices, 0, 1, -1, 0, 1, 0. Oh, look at this. That triangle is symmetric. And, I've got a symmetric domain. I've got a symmetric integrand. Integral is 0 by symmetry. Pen down, walk away. Or so a lot of students would do. Right? But that is not a valid argument. This triangle is symmetric over the y-axis. This function is only symmetric over the x-axis, as previously discussed. And tragically, these are not the same axes. So the symmetry argument does not work. Everybody see that? So in fact, not only does the symmetry argument not show the integral is 0, furthermore, the integral could not possibly be 0. Take a look at this. Over this domain, notice that on this domain, y is always positive. So let's just think it through. What's the value of this function? Well, x squared is always positive because it's a square. Y is always positive, therefore y cubed is always positive. This f that we're integrating is always positive, but not negative. So the integral couldn't possibly be 0. So watch out for the landmines. Right, it's real easy to get a little too excited about opportunities for symmetry. You see daylight, you run for the daylight, and you step on the landmine. So anyway, heads up. Be careful. Life does this to you sometimes, and it's very dangerous. Okay, going back to the previous example, I do want to say one other thing. I intended to go back and talk about this, and I forgot. So where did I come up with the x-axis? Why are we reflecting over the x? I pulled that out of thin air, right? And the idea is this: the domain being the unit disk, highly symmetric. I'm going to have a lot of opportunity for symmetry there. Let's worry first about this integrand. Let's try to figure out what would make this function odd, right? What kind of reflection, what kind of a line of reflection would make this function odd? And here's the way I thought about it when I was writing this example. I thought, well, okay, which one of these, what manipulation can I do to x and y that would make this function turn the negative of what it had been? If I were to exchange x for y, if I were to trade x and y, such as if I were reflecting over the line y equals x, would that make the value of this function be exactly the negative? No. This doesn't. Okay. What if I were to do whatever I have to do to turn x into negative x? Well, the problem is that negative would just get squared. Now that's not going to give me the negative of what I had. What if I figure out how to turn y into the negative of what it had been? Oh, well then that negative gets cubed. -1 cubed is negative. We're on to something, right? So the very first thing that I think is that in order for this to work, I can see that I want this to be the formula for reflection, right? So I don't actually motivate the line first. I motivate the formula for reflection first. And then I kind of reverse engineer it from there. Okay, well, this is what I wish a formula for reflection would look like. Second question, is there a line, reflection over which gives me this formula? And then you can go back and draw your little picture and say, well, I am taking points like this, and their reflections are turning into this. What am I reflecting over? And then you can see that it's the x-axis that gives that formula for reflection. Everybody see the strategy? there. So I encourage you all to think in terms kind of like this when you're looking for these opportunities. Okay, last quick comment, and then we got to move it on. Per the email that I sent out yesterday, I will not always announce. In fact, I will usually not announce in the statement of the homework question or the exam question when symmetry is a good idea. This is a tool for your toolbox, right? And you have to be on the lookout. That's how it is in life. Right? There is not going to be a label on the integral that says, hey, by the way, symmetry argument, right? So it is your job henceforth when you're looking at any integrals to, be your own, guide in looking out for opportunities to use symmetry. And just as a quick hint, in the exercises for this section, you may have already noticed in starting those yesterday, but there are several integrals in yesterday's in the assignment for this section. Several. I've forgotten if it's 2 or 3, but there's several where symmetry is by far the best method for evaluating the integrals. Okay, so heads up. Okay, moving along. So let's talk about coordinate systems again. And first, I want to remind you how polar coordinates works. Here's a kind of a picture of polar coordinates. If you've got a point here, right? The rectangular coordinates for that point say find that value x, that value y. And if I say that the rectangular coordinates for this purple point are x and y, then that tells you exactly where that point is. On the other hand, if I were to tell you that angle and that, I'm going to call it distance, but you know what I mean, kind of coordinate, because r could be negative, in which case it's back here. But if I were to tell you theta and r, again, that unambiguously describes exactly where that point is. So this is how we've thought of polar coordinates up to now. Polar coordinates is a different coordinate system for describing locations in space. I would now like to propose a different way to think about polar coordinates. There's big payoff in this point of view. Let's think of the polar coordinates conversion formulas that come straight out of this picture. Let's think of those as actually just being a function. Seems like a weird thing to do, but so we have a domain over here that's the r theta plane, and we have a target over here that is the xy plane. X and y, that I'm thinking of as the outputs, are computed as these formulas, r cosine theta, r sine theta, of the input variables r and theta. And notice, it's a little creepy to do this, but I've got an r axis and I've got a theta axis, and it's just a plain old, it's like it's an ST coordinate system or UV coordinate system, whatever. It's a kind of a rectangular coordinate system where r and theta are the variables. All right. So, it turns out that this function, the function that you get by interpreting the change of coordinates formulas as a function, this function is a fantastic change of variables function, a la the previous section. So we're going to use this as change of variables. We're going to pull back domains from the xy plane. We're going to pull back to interpret them as domains in the r theta plane. And it's going to be super. Now, in so doing, of course, we are going to have to take this function here now, and we're going to have to compute a couple of things. Most obviously, we're going to have to compute that stretching factor. Right? So let's go ahead and get that out of the way. It's just a single calculation. Here's what that Jacobian looks like. You got to take that determinant. Everybody should do this once in their lives. I did mine already. Y'all do yours. So write out that Jacobian directly from the original function. Compute those partials. Right? Take that determinant, and what you'll find is that you get absolute value of r. Because, of course, don't forget, the stretching factor is the absolute value of the Jacobian determinant. Okay. If you simply make the promise that you will always choose R to be positive, right? Even though technically we are allowed to make R negative if we want. If you just say, I tell you what, I promise, I hereby I will never choose negative values of R. Cool. Well, then the absolute value of R is now just R, which is very convenient. Okay. And so, if you want to do an integral in the xy plane, that dx dy just turns into stretching factor R times dr d theta, and everything else is just a matter of thinking about the bounds on the pullback domain. You just have to figure out what that pullback domain is, and you're going to have a new kind of an integral to consider. Okay, so let's consider an example. How would we go about doing this? How do we find a pullback domain? Here is a domain in the xy plane. Let's look at this quarter disk. And before we get down to it, let's take a pause on thinking about if this were a domain. If I were to just say, let's not get too fancy with it. Let's just chop this thing up, right? You can either do dx dy or dy dx, whichever, right? You're going to get square roots in your bounds. This equation is x squared plus y squared is 1. So you're going to solve for one of the variables or the others. That means your inner bounds are going to have square roots. That means that, as y'all have noticed, that when you do that inside integral and plug in those inside bounds, that outside integral, when you get to it, it's probably going to have square roots in it. And that's an annoying integral. So, undesirable domain. And that's why I want to pull back. I want to pull back through. Now, again, we're just trying this. We're going to try the polar coordinates conversion formulas as a change of variables function. I claim that we get this rectangle. And real quick pause before I justify that. Isn't that nice? Rectangles are awesome. The bounds are constants. Sweet. Okay, so let me try to justify this for you now. Let's think about this line right here. What happens if I take this line and plug it into the polar coordinates function? Well, this line, let's think about it. This line is r equals 1. Where is r equals 1 on this picture? Well, r equals 1 is the polar equation for a circle. Now let's think about this line. What does that line go to? What does it push forward to? Well, this line is where theta equals 0. Theta equals 0, starting with r equals 0, going to r equals 1, always with theta equaling 0. That's this line. You might consider, okay, what are these lines going to look like? These lines where, okay, each one of these has a constant value of theta. It's slightly increasing, right? But each individual line has a constant value of theta, and r goes from 0 to 1. Well, over here, what that looks like is like that. Each one of these lines represents a fixed value of theta increasing as you move along. And for each one, r starts at 0 and ends at 1. It's said you just gotta keep going through here. That line, theta equals pi over 2. Right? So you can see that this rectangle kind of effectively goes to that quarter disk. How are we doing? Now, some students are a little uncomfortable with the fact that this rectangle here is open, and what's going on over here. Let me point out that this edge, there is something really special about that edge. That edge, all the points on that edge, r equals 0. It's on the theta axis, so r equals 0. Which is just this, right? It's just the origin down there. So in the process of this rectangle kind of going over there, it's like we're kind of squeezing down. This yellow line all gets pinched down to a single point. You know, see what I'm doing with my hands here? It's kind of, we're pushing that down like that. Okay. Here it is. Okay. All right. So pull back. The domain, my original domain, this quarter disk, it's going to have square roots in the inner bounds. I'm not looking forward to doing that quarter disk. The pullback, though, is an easy rectangle. R goes from 0 to 1. Theta goes from 0 to pi over 2. So theta 0 to pi over 2, R 0 to 1, and there's my integral. Now I do have to, whatever this function, this integrand is, I'm going to have to plug in everywhere I see an x, I'm going to have to put r cosine theta. Everywhere I see a y, I'm going to have to put r sine theta. My integrand might get a little uglier. It's true. But my bounds got a lot easier. Okay, so we're using polar coordinates as a change of variables function. Okay, good news. It's always going to be this for the stretching factor. The stretching factor is always going to be r when you're using polar coordinates, because after all, there is only one polar coordinates. If you're using polar coordinates, you are using the same change of variables function that we just got through doing. We've already done the calculation. The stretching factor is r. Don't forget, r's got to be positive. Not allowed to choose negative r's anymore. That's off the table. No longer. Very dangerous. So you don't have to do this calculation every time. You do it once in your life, and you're done. So henceforth, you should just remember dx dy is r dr d theta. Just memorize that, right? Furthermore, I advise you, don't write. It's very tempting to say, okay, I want to do this conversion, so I'm instead of dx dy, I know I'm going to get dr d theta. Let me write down the dr d theta, and then I'll start thinking about the details. I think that's a mistake. Because what happens is students get bogged down in thinking about what are these bounds, and then they forget. This happens so often. Students will just flat forget to think about the stretching factor, and they'll just inadvertently leave off the r, which of course is wrong. Importantly, like dramatically, very importantly wrong. That's the whole sort of big point of change of variables, is that stretching factor. Right? So my advice is, and I follow this advice myself as much as I can make myself do it, just don't ever write dr d theta by itself. Why would you? That's never going to be a thing. It's always going to be r dr d theta. Write them down together. And then you won't forget. So that's the advice. Good luck remembering. Okay. All right, let's talk about cylindrical coordinates. Same kind of a thing. You can think of cylindrical coordinates as, kind of a way of thinking about where points are in the XYZ space. Or you could just take those formulas and say, I'm going to view them as a function from R3 to R3. The input variables being R, theta, and Z. The output variables being X, Y, and Z. And now I have here a change of variables function. And again, it's very handy. Change of variables function. You can go through and compute your stretching factor. No surprise, being as cylindrical coordinates is kind of, remember how we were talking about it's kind of sort of polar coordinates in R3. Right? And so no surprise, the calculation looks a lot like that older calculation. You do get absolute value of R again. Again, always promise to use R positive. At which point it's just R. Okay. Okay, so let's see here. Where's my, here we go. So, so for example, if you have this odd fellow here as your domain, right? This kind of, it's like half of a cylinder, half of a part of a cylinder. If that's your domain in the XYZ space, it's going to be square roots. Unavoidably, if you do it in rectangular coordinates. But let's pull back through this cylindrical coordinates, change the variables function. And I claim you get this box. How do I know? Well, let's think about this box one face at a time. That face, r is 1. R equals 1 in cylindrical coordinates in XYZ space looks like this. That's r equals 1. Let's see here. What is this face there? That is theta equals 0. R goes from 0 to 1. Z goes from 0 to 3. So that plane goes to that plane. Again, you can think of kind of a succession of parallel planes here, and where do they go? And, well, you're going to be increasing the values of theta a little bit each time. See what I'm talking about? It finally ends over here where theta equals pi, which of course is, okay, that was terrible. I'm going to do that again. Which ends back there. Everybody on board? Okay. So, which would you rather do? Would you rather do an integral over here? Probably not. You should prefer to do the integral over here. It's a box, constant bounds. Everybody wins. And so now it's just a matter of, let's see, we already computed the Jacobian determinant. Now it's just a matter of plugging in everything that we've just figured out. dx, dy, dz is stretching factor times dr, d theta, dz. We know the stretching factor is r. So again, I urge you, don't, in the spirit of, well, I had a dx, dy, dz, let me just, I know I'm going to have dr, d theta, dz, and I'll just write down the dr, d theta, dz first, because I know it's going to be there. Big mistake. You just put yourself in a situation where you're very likely to inadvertently forget your stretching factor. Don't ever write down dr, d theta, dz by themselves. It's never relevant outside of there also being an r there. So write down r, dr, d theta, dz all at once. Let's see here. Yeah, and then of course we have to plug in for x is r cosine theta, and y is r sine theta, and z conveniently is just z. Okay. And now we've done the pullback. Our new domain is this box that we drew on the previous page. That's a rectangular box. It's got nice square bounds to it, constant bounds. And now this integral is much easier, at least in the sense of the bounds. Okay. All right. Is everybody on board? Everybody happy? Okay. Okay, let's see here. Yeah. Okay, so hopefully no surprise. Spherical coordinates can be thought of as a change of variables function. I'm going to go a little quicker through this because this is our third time of implementing morally the same idea. Conversion formulas can be thought of as a function, right? So we think of rho, phi, and theta as part of the XYZ space, but let's think now of rho, phi, and theta as being their own axis system. The conversion formulas are a change of variables function. Let's compute the stretching factor. Again, everyone should do this at least once in their lives. That Jacobian determinant is this. I really do think it's a very healthy exercise. Compute that Jacobian on your own. It's just a bunch of partial derivatives. It's no big deal. It's good practice in making sure that you are good with the structure of the Jacobian and that you're proficient with computing partial derivatives and that you remember all your trig calculus. Right? So that's a good exercise. Then compute out this determinant. I did mine, right? Everybody's got to do this once in their lives. It's actually not that bad. trig identities pop up all over the place. Look for numerous instances where sine squared plus cosine squared is 1. Right? But if you crank out this determinant, monstrous though it appears at a glance, it simplifies dramatically. And what you get is rho squared sine phi. Okay. So I want everybody to do that calculation on your own. Exercise for the reader. Now, there's a common misconception out there. A lot of people look at, look, for polar coordinates, you have to promise that you'll always choose R to be positive to get rid of the absolute values. And so, look, in spherical coordinates, rho is kind of playing the role of R, sort of. The rule must be that we have to choose rho to be positive. Because rho is kind of like R, right? Not so. Let's look at this formula. Right, what do I have to know in order to know that this absolute value can just go away? Well, I need to know that what on the inside is positive. And whether or not rho is positive does not matter one little bit. Rho is going to get squared inside of here. The rho squared will never be negative. Rho is not the problem. The fact that it is the analog of R from polar coordinates, irrelevant. It's not the point. What we need to do is to make sure that this factor will never be negative. Right, so we've got to think through, values of sine. We're going to have a constraint on phi. What constraint on phi will ensure for me that sine phi is always non-negative? And so you got to think it through. And the answer, of course, is that phi has to be between 0 and pi, and that's the rule you have to adhere to. Unless you just want to deal with absolute values, you don't. Right? So phi has to be between 0 and pi. Hey, good news. Those are the values of phi that we all prefer anyway. Those are the obvious, if you will, everyone's first choice value of phi. So again, there is a kind of an analogy with polar coordinates. It is again the case that our obligation related to the absolute values is to do what we want to do anyway. Right? It's just that here the point is that the obligation relates to phi. Okay. Alrighty. So let's look at this picture here. Right? Let's suppose I have a half ball like this, and we have looked at domains like this, and we've tried to write out the corresponding rectangular, the iterated integral, what are the bounds, and got square roots everywhere, and they're quite tedious. Right? So what we're going to do here is think in terms of spherical coordinates, and notice that rho equals 1 is that. Right? Now, I got to think through, what's going on with the phi and the theta. Let's think about that right there. That's phi equals 0. Let's see. Hang on a second. Sorry, wrong one. Let's think about this rectangle here. That rectangle is where theta equals 0. I've drawn theta vertically here. So this is theta equals 0. In the plane theta equals 0, I've got rho going from 0 to 1, and I've got phi going from 0 to pi over 2. And that means that I'm looking, so inside of theta is equal to 0, I've got rho going from 0 to 1, right? But then phi going from 0 to pi over 2. So altogether, what I've really got is this kind of quarter disc, so it's sort of a half of a slice through that half ball. And now you can imagine what happens if you sort of move up. Right? So what is this? And it's going to look a lot like that. It's just going to be kind of the same sort of thing, but for a larger value of theta. Now theta has increased a little bit. Well, if theta increases, then, okay, so now you're looking at something like that. It's like you've just kind of rotated around the z-axis a little ways. So if you want to make the entire half ball, you can see from the picture here that I need these sort of half slices to go all the way around. So I need theta to go all the way up to 2 pi. Let's see here. I'm going to, in order to make this go all the way around to 2 pi, I need for theta to go up to 2 pi. Right, where this then has this same purple image there. Yeah, everybody good? So the pullback of that domain is this rectangular box. And so using this, using spherical coordinates as a change of variables function, the final punchline, dx, dy, dz is, again, write this all out all at once. Right? Don't write down the d rho d phi d theta, and I'll come back to the rest at some other future time, because of course I could never possibly forget, right? Absolutely can forget. Write this down all at once. Deep breath. Rho squared sine phi d rho d phi d theta. All at once. Don't ever write this down by itself. Why would you? It's never a thing. Then, of course, you have to plug in for x, which is that in terms of polar coordinates, spherical coordinates, y, which is this, and z, which is that. That's just plugging in, so no big surprises there. Our new pullback domain that we just discussed on the previous page is a rectangular box. There's the bounds, and we have ourselves a new integral in spherical coordinates. Much preferred bounds. Okay, so that's a large part of doing integrals in a different coordinate system. I am going to simply show you a different way to think about it now, on one that's a little bit more artistically convenient, and that is to simply try to see the coordinates, the ranges of values of the coordinates, directly in the xy plane. So now here's our first example. Our first example was in polar coordinates, and we were looking at this. We pulled it back to this rectangle. We drew the pullback. We then looked at the pullback and said, okay, well on this pullback, theta goes from 0 to pi over 2, and then for a given value of theta, r starts at 0 and goes to 1, right? We did the slicing over here on this picture of our new domain. After all, that is our domain. We went to a bunch of trouble to arrange to have this nice domain. Of course, we're going to slice up the new domain. Okay. So the cool insight is to notice that actually every part of that process, the whole slicing process, you can actually see it over here. So for example, theta goes from 0 to pi over 2. Okay, well, yeah, sure, but here's what theta equals 0 looks like. Here's increasing values of theta. There's theta equals pi over 2. You can see these bounds. Theta going from 0 to pi over 2 without drawing that picture at all. Okay, then, having done that, for a given value of theta, well, here's my value of theta. There's my fixed value of theta. Let's say I'm just viewing it in the xy plane. The range of values for r. Well, r starts, no, I'm not going to do it over here. R starts there where it's clearly 0. And instead of going over it like that, I'm going to say we go over like this, and we end there where r is clearly 1. In fact, I had that picture already drawn over here. Sorry. So you can see the bounds r going from 0 to 1. You can see it over here if you want to for whatever reason, but better, you can see it right there in your XY plane picture. Okay, so here's what I propose. And by the way, this is what everybody does. Okay. The idea that I want to encourage you to think about is that understand that we are, of course, doing a pullback. We are finding a new domain by way of a change of variables function, stretching factor and all, right? But you just don't need to draw the picture of it, right? We don't actually need to look at it. In fact, just for visual effect, I'm going to scratch this thing off. Let's just forget about that, phooey on that. I'm just going to say, look, I'm going to do this integral on this quarter disk. I'm going to do it in polar coordinates. So, change of variables function, pullback, stretching factor, that whole thing. There's some new domain. I'm not going to draw a picture of the new domain. That's just why. Everything I need to see about the new domain, I can see here. Just make sure to understand what slices look like. Theta, theta going from 0 to pi over 2 is perfectly visible right there. And then on a fixed value of theta, r going from 0 to 1, perfectly visible right there. So we're going to do a change of variables. We're going to pull back the domain. We're just not going to actually visibly represent that at all. We're just going to infer what we need to know about it directly from the picture. So this is what they mean when they say we're going to do the integral on this quarter disk in polar coordinates. They mean we're going to do exactly what we would have done with a change of variables, and all the information that we need is already visible. So why really write it down? Okay. So here's another example. Let's suppose that your domain was this half disk. Polar coordinates would be a fantastic change of variables function. I suppose you could draw that pullback rectangle. You think about what is the rectangle that whose image would be this, and you can try to draw that and push it forward, all that business. But it's much easier to just instead say, look, here's what a theta slice looks like. Theta slices look like this. And theta keeps going along until I get to there. So theta goes from 0 to pi. Don't really need the picture in the r theta plane. Then for a given value of theta, whatever value, arbitrary value of theta, here's an arbitrary value of theta. Call that the theta slice. R, well, it clearly starts there. And r increases until you get to the edge. So r goes from 0 to 1. And all the bounds that you need, what's the new theta bounds for your pullback integral? What's the new r bounds for your pullback integral? You've already got them. And here you go. Theta goes from 0 to pi. R goes from 0 to 1. Notice there's my r. I didn't forget to write down my r. Always write this down always write this down together all at once. R, d, r, d, theta. Again, otherwise you'll forget. Okay, yeah.
Can d, r, d, theta be switched?
That's a great question. You can do that. It's very rare that it's helpful. And it's almost always the case that it's counterproductive. Yeah. So this is one of these situations where the good news is it's almost always the case that you want to do dr d theta. And roughly speaking, the reason why is because the shapes that we tend to want to deal with in practice most of the time are shapes where it's easier to solve for r as a function of theta than it is to solve for theta as a function of r. Right? So we saw a lot of when we were talking about polar coordinates, certain kinds of circles will have an equation like r equals sine theta. Well, you could say theta equals arc sine of r. Ugh, but now you're dealing with inverse trig functions, and nobody prefers that. You see what I'm saying? Yeah, so it's very rare that it's a good idea. I have an example of that written in here somewhere. Yeah. Oh, yeah, here it is. Yeah, and you can see you end up with arc cosine there in the bounds, and it's just, yeah, we don't need this. It's so rare that this is a good idea, that you put the theta inside of the R. It's so rare that it's a good idea that I'm just going to say for Math 212 purposes, just don't ever do it. It'll never be a good idea in Math 212. Yeah.
And that applies with cylindrical and spherical as well.
It's similar, but let me get to that. Yeah, right. Okay, let's see now. Did I just gloss over no, I think I covered all that I wanted to here. Yeah. Right, okay, so, yeah, let's go to cylindrical coordinates. Here's what the slices look like. Now, in polar coordinates, theta slices, constant value of theta, it was just kind of rays emanating out of the origin. That's what a theta slice looks like in the xy plane. Here's what cylindrical slices look like in 3 space. What you might call an R slice. Now keep in mind, a slice means a constant value of that variable. So here's what an R slice looks like. That's where R equals a constant. That's kind of weird. Right? Here's what a theta slice looks like. That's kind of nice. And here's what a Z slice looks like. That's kind of nice. So, same story. You could pull back, draw your pullback domain, and then slice up that pullback domain in the R theta Z space. But everything you need to know comes from just slicing in XYZ space. Just make sure to slice appropriate to the coordinate system. And if you're slicing in cylindrical coordinates, this is what your slices look like. So let's see here. Here is an example. Let's think about this as a domain in XYZ space, and I'm going to use cylindrical coordinates. By the way, it's kind of round, you'll notice. Right? So if I were doing this in rectangular coordinates, the roundness would pretty much ensure that one way or another somewhere I'm going to have square roots in my bounds, and so this is not appealing. Okay, so arbitrarily, let's do our Z slices, air quotes first. So I'm going to do Z slicing on the outside, and a Z slice of that cone is a disk. Right? By the way, then Z goes from, wherever the bottom of the cone is to wherever the top of the cone is, and I think I remember it was 0 to 1. In fact, let me find the statement of the question. Yeah, so the vertex is at the point 0, 0, 1. Base is the unit disk in the XY plane. Yeah, so Z goes from 0 to 1. Then, for a given Z slice, let's think about our theta slices. Another thing I should write down. Sorry. Let's be explicit about our order here. So there's my ordering. Note I've put my stretching factor in there, just as a matter of good form, so I won't forget. We've already got Z bounds. Z goes from 0 to 1. Now, next, I want to ask, what are my theta bounds? What's the range of values of theta? Well, theta starts off at 0 and goes all the way around to 2 pi. Then, for a given value of Z, already drawn, for then a given value of theta, let's look at this theta slice of our Z slice, and I want to know what then is the corresponding range of values of R. Well, R starts there on the axis, where R, of course, is 0, and R goes out to this point on the cylinder. And what can I say about that point on the cylinder? Well, you have a couple different options. You could write down the equation of the cylinder. I like to make the observation that R is independent of theta because of symmetry, and that if I look in this plane where theta is pi over 2, notice that the formula, well, the relationship between R and Z there is a straight line, and it's a real easy straight line because that's 1, this is 1. So this is the line R plus Z equals 1. In which case that means that R is 1 minus Z. Okay. And so here they are. Here are those bounds. Z from 0 to 1, theta from 0 to 2 pi, R from 0 to 1 minus Z. Don't forget the stretching factor. Again, there it is. There's that R that I put in there right next to my dr d theta dz. That R, by the way, here's another mistake students make sometimes. Some students take my advice a little too seriously to always put the R with the dr d theta dz and then feel like somehow that means that it stays with the dr d theta dz, and somehow, I don't know what the reasoning is exactly, but they won't put it into the integrand. Of course, the whole point of writing it down is so that it will make it into the integrand. It's not some sort of little cosmetic, window dressing there just for the appearance, right? R is part of the integrand. And you can see that factor of R in here. Okay, spherical coordinates. Here's what spherical slices look like. Oh, I'm sorry, I got ahead of myself. Sorry. Let's talk about the order that you should use. This is the order that I used here. I did my dz slicing on the outside, and then I did dr d theta on the inside. Now you'll notice right away I've got R on the inside of theta. And per your question, I think that's always a good idea. dr should always be inside of d theta. Also, because R and theta, they're kind of right next to each other. They're part of we're thinking of them together and how they sort of tell you about which way you're going sort of in the XY plane. I think it makes sense for them to stay contiguous. Right? So I suggest you think of your options as this. There's dr d theta, always in that order, and there's dz. And your two options are which one of these pairs goes on the outside and which one goes on the inside. You'll see your other reasonable option is this one. Right? So you can have dz inside of dr d theta as opposed to dr d theta inside of dz. And really none of the other options give you any value that you need, and some of them are bad. So I suggest always choosing one of these, and I've yet to see a Math 212 problem for which the best choice is not one of these. Okay, so cool. All right, you know what? Why don't we go ahead and take a pause right here, and we'll take a 10-minute break and pick up here and talk about spherical coordinates and go on from there. Okay, see y'all in a few minutes.